Hello everyone, my name is Jonathan Mee, and this will be the first of many videos for tutorials of design and build that I am making for Team 3647. So to introduce myself, I am the head of design and head of build, and I have been for the 2017, 2018, and 2019 seasons, and I have also been head of electrical in the 2016 season. So I will be teaching in this lesson about how to use HSMWorks, which is a CAM software. I'll get into that later. It's essentially what we use to go from a CAD model of a part to running the part and making it on the CNC. So the CNC that we have is the Cnc Router. It's the Velox VR-5050. It is a 50 by 50 inch CNC router, which we purchased right before the 2018 season in December. In the description, I will also include a Google Photos album of videos and photos of our CNC and using it. So what a CNC is a computer numerically controlled. So it's a computer that actually controls the CNC. There's motors on each axis versus something like a manual milling machine, which a human operator controls. With the CNC, you can you can have much tighter tolerances, since it is a machine that is machining it, and do things that typically a manual machinist would not be able to do. The benefit of a CNC router over, say, a CNC mill is that with the CNC router, we're able to do sheet metal, such as this. This is a belly pan for a 2018 robot, and we are able to cut out these sheets of metal, and it is it's really quick and it's very precise. So here's a short video clip of the CNC actually working. And so as you can see, there is the router part of the CNC, and the router is, or also referred to as a spindle. It has the end mill, and the end mills we use are typically these 3/16 inch single flute carbide end mills. As you can see, it spins, and then the CNC moves to use the end mill to cut the material out. So next part I'm talking about is the actual software that we use to create the code that controls this machine. So the workflow goes from SolidWorks to HSMWorks, and then to the CNC. So HSMWorks CAM software, computer-aided machining. We use this in SolidWorks to generate the code. So to get it, you can just go here. This link will be in the description, and you just, if you're a student, you can get it for free for 3 years. And it is an add-on to SolidWorks. So once you install and download that, you will have a new tab on the top. In assembly and parts, it's called the CAM. So with the CAM software, there's a couple different operations we can do. We typically stick with 2D milling and drilling. So drilling, it's self-explanatory. We drill holes. So you see these holes where these screws are. We use the center drill first. So center drill is one of these. So these things are precise, and they allow us to put little dimples in the material, which we will then follow up using a drill bit. And then once we put the drill in, we will screw down the actual material to the table, and the table is, we use an MDF board, which has been surfaced flat. As you can see in this photo, we surface it flat, and then we use the screws to hold the material down into the board. So that we use the drilling operation here for it. We use the drilling operation. And then the second type is 2D milling. So 2D milling, there's a couple different options, ones. We typically stick just to 2D contour. So 2D contour is what you see in here. So it cuts out a contour by outlining it. So all of these were cut out by outlining it. There's also 2D adaptive clearing, which instead of cutting out just the contour, the end mill clears out the entire area. it's typically a bit slower and it's not as good, not as quick, which is a key part in the build season, since we only get 6 weeks. So let's jump right in with the part. So the part that we will be using is from our 2018 robot. It is an elevator. It's an elevator part. It's a gusset. So typically we make gussets. Gussets are our most common part that are made on it, since it's made out of sheet metal. So this part is made out of 1/8 inch 6061 aluminum. So once you plop the part, we like to do this in assembly, so we can make, instead of having code just to cut out one of these, we can cut out multiples of these. So the first thing you're going to want to do is put a sketch. Just put a sketch on the top of the part for our stock boundary. So the stock is the material that we cut out of. So stock, since we have a 4x4 foot router, we like to buy 4 foot by 12, 4 foot by 1 foot long pieces of aluminum stock, sheet stock. So what we're going to want to do is you're going to want to dimension the sketch to 48 by 12, as you see here, and you also want to dimension it to be, so this dimension here is actually the center circle, about 1/4 inch of space on each edge of the part, because the stock is not perfectly aligned to the table, or to the axes. So we want to get rid of that error by adding space, and also because when we put the stock, when we mount it to the MDF board, we put holes in a perimeter around it and put screws there. So we don't want to hit the screws or have our parts be cut off by holes in them. So once you dimension your sketch, you're going to want to linear pattern or copy paste, if it's like an odd shape, multiples of the parts. So components pattern. So I'm going to leave about 1/4 inch between each of these parts, and I'm going to do 6 of them this time at a time. So next, you're going to want to create a coordinate system. So coordinate system is used for the CNC to know where the 0 is. So like the 0 of the part. So you're gonna choose references for the axes. So the z-axis, that's vertical. The y-axis is the long axis, and the x-axis is this direction. So the z-axis right now is actually. So you might have to flip these a couple times in order to get them to line up properly. There you go. So once you create that coordinate system, you're going to want to create a job. Now, a job is sort of a folder of a collection of operations. So for this, the job type, it's milling job, CNC milling. And the model, you're going to select the parts that you will be cutting out, and see this yellow border creates a stock border. And then for the coordinate system, you're going to want to select the coordinate system that you just made as the 0 point. So now once you're done with that, you see on the far right side of your property manager, you'll see there's a new job now. So the first thing we will do, as I mentioned earlier, is use the center drill to make divots, little dimples for all of these holes. So you're going to want to go to drill, select drill, and then for the tool, we'll be using the center drill. So I have my own library of tools that I have created. I will be also including this. So these are the tools most common tools that we use on our team. So the first thing is the 316 center drill right here. So as you see, it pulls up the router part as well as the center drill. With this part library, I'm able to set these feed rates and such. So a feed rate is essentially how fast you're cutting. So the feed rate I use for center drills 15 inches per minute. So that means the CNC router will move in a minute. It'll move 15 inches, which is what we use for drilling. So the cutting feed rate is how fast it cuts. The lead-in feed rate is in a part if it has to lead in, sort of like a preparation cut. That's the speed. The lead out is the opposite. the ramp feed rate. I'll get to that one later. And then there's the plunge feed rate. Plunge feed rate, this is the key thing here, is because this drilling operation uses the plunge uses a plunging maneuver, which is straight up and down. And then there's the retract feed rate, which is how fast it backs up. Now our CNC, it maxes out at about 100 inches per second, but you really don't want to run it that fast, because it depends on the CNC rigidity and like how fast your spindle is spinning, which you can set here. But this actually does not matter at all, because our router is an actual like router, and it has the speed gauge on the RPM settings physically on there. If you were to have something like a VFD spindle, which is computer controlled by the CNC, something like this, then you would want to have this RPM be accurate. And this RPM here is actually accurate. We run our router at 10,000 RPM, spin on 10,000 RPM for drilling. So this next tab is the holes. So you're going to select one hole. So this is a number 10 hole. This one's a 1/4 inch hole. But once you select the hole, you're going to select same diameter as well. And it'll select all the same diameter ones. These ones are 3/16 holes. These are for rivets. Number 10 holes are for bolts. And then there's another 1/4 inch hole for bolts. So you just want to verify that all the holes have been selected. Next one is, this is your heights. So the retract height is, all of this, the retract height, if you hover all of these, you'll have the little pops up explaining what it is. The ones you want to keep an eye on are bottom. So the center drill doesn't actually, we don't want it to go all the way through the material. So what I will do is, from selection, I will set the offset to be 50 thou below the top of the surface, which means the center drill will go 50 thou. You see the green line, that's the path that it takes. The center drill will go 50 thou into the material, not all the way through. And this last one is, you ignore that one for now. So you can also, so it creates, as you can see, a new one. You want to name it, so call this the center drill. I also like to add a number to it, so the CNC operator knows which programs to run and in what order. So I'll add 1 because it's the first one you want to run. If you click on this and right click it, you can also simulate it, so you can watch the CNC actually do the path, and you hit show stock as well. It shows the material. And you always want to simulate your operations to make sure that they will run properly. You just speed through it and just check the end product. So see, that's proper. The center drill just makes divots in each of the hole locations. Next is the 2D milling. So we'll use contour for this because we want to cut the outlines for each of these. The tool we'll be using is the 3/16 flat end mill. For 1/8 inch plate, we like to go about 30 inches per minute. 30 inches per minute, cutting like the outlines. And we like to cut, there's 2 new terms that you need to know, is the depth of cut. So how deep is each pass of the end mill going to cut? And the width of cut is what's the width of the path. For contour, it's always the diameter of the end mill that you're using, which is 3/16 in our case. For the model, you want to select just the outlines. So you'll see that there's an arrow that pops up, which shows sort of the, not which direction it's cutting, but which side of the line it will cut on. So these ones are correct. These ones, we don't want it to cut on the inside, so you just hit reverse, and it'll switch it to the outside. Now for layers, one very important thing is, you see, right now, it'll cut just the very bottom of it. We do not want that. We want it to cut past the bottom of it, so that we don't leave like thin foils of aluminum. We didn't really know about that when we were cutting this part. This is one of our first parts. So you'd see it's sort of, this didn't cut all the way through. We want to ensure that it cuts all the way through. So we'll want to set the bottom from the contour, which is what you just selected. We want to cut down an extra about, oops, hit that key, 30 thou. So you see, it'll cut an extra 30 thou on the bottom. Next, you're gonna want to, so with this, typically you can ignore this. Except for everything else you can ignore except for this option called multiple depths. I'll get into, for this one, it's an 1/8 inch material, which means we can cut all the way through. In the next part example, we will be using this. So multiple depths lets you set how many layers you want to take to cut the material. So if we use a thicker material, you want to take multiple layered cuts. And then this final one is called linking. So we have the lead-in. So lead-in, sort of, as I explained before, it's the preparation when it leads into the cut. You can leave these alone. Lead out, when you're cutting these outsides, you're going to want to disable the lead out. And I will explain that in 1 second. But the most important thing on this page is called ramping. Ramping essentially allows you to ramp the cut in. So typically, if you don't check that, what the tool will do is it'll go straight down, plunge straight into the material and start cutting. Plunging with end mills, bad idea. You're going to want to ramp it. So ramp, the only setting you want to change here is the ramp clearance height. So this is the height at which it starts ramping into the part. Like I said, about 30 thou above the part. So that will generate the toolpath, and then we can watch the simulation. So as you can see, the part, see how it slowly goes down into the material. Slowly cuts down. That's good because it's bad to plunge, and ramping is good. And see, it cuts all the way around and then cuts out the part where it didn't cut all the way through. So we just want to make sure it doesn't works properly. Okay. So it's contour and center drill. But there's one more thing you need to do, one more tool. And that's the actual holes, which I forgot to do. So the tools, we use the 3/16 drill bit at 12 IPM, 12 inches per minute, plunging down, 12 inches per minute with the 3/16 bit drill bit. Now because since we're making the actual holes, we're going to want to drill all the way through. So you want to select this check mark, drill tip through bottom. So this is how much deeper from the bottom of this you want to go. I like to go about 0.1 inches past the bottom of the part. So that'll ensure that the goes all the way through, and then you're going to select all the holes. Every hole that is at least as large as at least 3/16 in diameter, you're going to want to select, which includes the quarter hole and the number 10 hole. So I'm going to simulate this as well. You can see, drills all the way through. And then we're going to name these. So the contour is actually the last operation you do. So we can actually move that up one. And then this is 2 3/16 drill. Center drill. So the reason why you have to do the drill first is so when, as I mentioned before, we have holes in the big stock, the 4x1 stock, and the holes and the screws that hold it down. Once you do the center drill, right, you mark the holes, and then you use the drill, you drill all the way through. The CNC operator has to stop, screw all these screw holes down, or at least enough so that the part is held down, because if you skip this step and you go straight to the end mill, your parts, once you cut them out, they'll just go flying. But you can see in this right here, see how that part, if you didn't, so this part that comes out is an excess part, and it's a part that we wanted to get rid of. But if that was the part that you wanted to keep, and you didn't have any means holding it down, it would just fly straight out, which is bad. And so now you have all three of your operations done, and then next step is to export them. So right click, post process, and for this post configuration, this one right here, you want to use Mach 3 mil. On the CNC, which I will be making a video later on about how to use it, we use Mach 3, it's software that controls the CNC. So you're in Mach 3 mil, and then choose an output folder and then a name. So you want to maintain these names. So typically output folder, I usually use, we use the USB to transfer the files from the computer that is running SolidWorks and doing the HSMWorks onto the computer that controls the CNC. So then once you have this all set, you just hit post, and then you can save the file. And do that for each of these three individually.